Here's where I'd like to start today. If I give you f of x and g of x, there's certain things that we need to be able to do with these two functions. Okay? First thing I need you to be able to do is that. What's that want you to do? Yeah, add them. So if I take f of x, 3/4 roots of x, and g of x, I should be able to add them together. Now we know properties of radicals. We know about the properties of radicals, right? Okay? Properties of radicals say if my radical is the same, what can I do with the numbers in the front? Well, what it asks us to do, right? So if it asks me to add this, can I add 3 and -7? Yeah, because my radicals are the same. So what am I going to get when I add 3 and -7? -4 4th root of x. And that's the answer. Yep. What about f minus g of x? Knowing our properties of radicals, can I say f minus g of x? Okay, so I have 3/4 root of x minus -7/4 root of x. But that makes it a positive, right? Subtracting a negative. So I end up with 10/4 roots of x. Everybody okay with that so far? Okay. What if I give you a different value of f and g? Are you okay with that? If you're not, just get over it. We'll be fine. Here's the value for f I want to use this time. And here's the value of g I want to use this time. What I'd like you to be able to do, whoops, there, multiply them. Can you multiply these? Okay, so that's 2x to the third times a -3rd root of x. It kind of looks like I have like bases, right? I've got an x here and an x here, and if I have like bases, I know from my exponent rules, if I have like bases, what do I do with the exponents? Add. But this looks too messy for me, so can I change it a little bit for you? Okay. Based on what we know from our exponent foldable back here, remember we talked about this, and we've talked about it, and we've talked about it. Okay, it's time to talk about it again. All right. This is really going to stay the same, isn't it? It's this one that's going to be a little bit different. The numerator is the power, so that's to the first power. The denominator is the root. You okay with that? Okay. Now that I have a like base, what can I do with the exponents? Add them. So how do I add 3 and 1/3? How do I add fractions? I need a common denominator. So I'm going to come over here to the side. I'm going to say 3/1 plus 1/3. I made 3 into a fraction. You okay with that? Okay. So what would my common denominator be between 1 and 3? 3. So to make this one a 3, I multiply it by 3. And to make this numerator a 3, I multiply it by 3 because I have to multiply it by just a value of 1 so I don't change the actual value of the fraction, right? So this fraction ends up being 9/3 plus 1/3. So let's come back to this problem now. If I'm multiplying, I actually get -2, that from the negative, that from the 2, and then I get an x. Right? That's my base. What do I do with the exponents? Add them. What is 9/3 and 1/3? to the 10/3. Done. Yes or no? You good? What's the last one I'm going to show you? Okay. F over g, or f divided by g of x. So what's that going to look like? 2x to the third over, now I want to be proactive here. I want to think about what I'm going to write before I actually write it. I could go ahead and write negative cube root of x, right? I could do that. But when I divide fractions with like bases, what can I do with the exponents? Subtract. Well, if I know I'm going to end up needing like bases with exponents, shouldn't I go ahead and write negative x to the third? Because you know those are the same things, right? We just had to figure that out for this problem up here in multiplication. In order to do anything with these, I'm going to need like bases. Now I have like bases. Well, I already know what 3 is, again, because of this previous problem, right? So this is not really 3, it's really 9/3, even though that is really 3, right? So I'm going to have negative 2, because I've got the negative here and the 2 here, because I'm just dividing those, right? And then I've got x to the 9/3 and x to the 1/3. What do I do with those exponents? What is 9/3 minus 1/3? Done. Can you do operations on functions? Do you feel comfortable doing function operations? Adding, subtracting, multiplying, dividing. Okay. That's one of the 3 things that you're going to be asked to do for your lesson today. All right? The next thing you're going to be asked to do for your lesson today is evaluate. What if I tell you x equals 16, and I want you to go back to this function right here? How would I evaluate this function at 16? I substitute it in, right? Plug it in, substitute it. Substitute's a better math word, right? So I have negative 4 times the 4th root of 16. What is the 4th root of 16? What times what times what times what equals 16? 2, right? 2 times 2 is 4 times 2 is 8 times 2 is 16. So the 4th root of 16 is 2. Well, if the 4th root of 16 is 2, what is 2 times negative 4? Done. I said done. I substituted in the 16 for the x, right? I'm evaluating this equation at x equals 16. So I substitute the 16 in here. I think about what is the 4th root of 16. I think about what times what times what times what. 4 things have to multiply together to be 16 for me to be able to take this. I know that 2 times 2 times 2 times 2 is 16, so the 4th root of 16 is 2. The value of this part of the problem is 2. All I have left is 2 times negative 4, and I know 2 times negative 4 is negative 8, so that's my answer. Okay? Could I evaluate this function at x equals 16? So 10 times the 4th root of 16. We know the 4th root of 16 is 2. So what's 2 times 10? Done. Okay? No?
So,
Which part?
whenever we put that 2 under there, are we saying like divided by, or is that just there to say like show our work?
That's me showing my work. That's why I put the curvy line right here to say the value of this part of it is 2. I'm sorry I confused you.
So you do what's in the middle, in the inside,
In the root first.
and then whatever that is, you multiply it by the outside.
Yeah, and what if it said minus 5 right here? I would do minus 5 then, right? And say 20 minus 5, and that answer would be 15.
Okay, so you would then multiply your outside and then you would do
Mm-hmm. Better? Good. What if for these problems down here I told you x was 27? Could I do that? So if I come down here to this is my function, right? It's my two functions multiplied together, so this is my new function. I would say negative 2 times 27 to the 10^3 power. Well, the numerator, is what? The power. And the denominator is the what? What is the cube root of 27? What times what times what equals 27? 3. What is 3 to the 10th power? Guys, what does a power mean? Does it mean multiply? Not 3 times 10. No, it does not. You've known that for a long time. I don't know why you're acting like that. 3 to the 10th power means 3 raised to the 10th power. 3 times 3 times 3 times 3, 10 times. Yes? Okay. But then I have to multiply that by negative 2 to get my answer, right? Because this number right here just is accounting like that part of the problem, right? So to get my answer, I multiply it by negative 2. So that is 118098. So 118,098. So here was the reaction I got earlier. Well, that can't be right. That number's too big. I think you've been conditioned that if you get a number like this, the answer has to be wrong. There's nothing wrong with this answer at all. It's just big. And really, it's relatively big. If I ask you what's the distance between the Earth and the Sun, that's not a big number at all, is it? Not compared to that. So numbers like this are okay to get for answers. That's okay. Don't freak out. No freaking out. Oh no. Can we evaluate this one right down here also at x equals 27? Okay, so I would get negative 2 times 27 to the 8/3 power. 3, okay, what's the cube root of 27? 3, so 3 to the 8th power. 3 raised to the 8th power. 6,561 times what? Negative 2, because that's part of the problem, right? So that answer is 13,122, except it's a negative. I forgot my negative. Uh-oh, I forgot my negative up here. Wait, let me fix that. Ask me your question.
So before you just keep on asking, like, can we do that by 27?
Mm-hmm.
When is there a point that we can't?
What if it said x equals 25? Could we take the cube root of 25?
Yes. No. Wait, what?
I would get a decimal, right? It wouldn't be a nice number like 3. You could still get an answer. I was mostly just saying, let's do the next part of the problem. I apologize for asking your permission. You okay? Okay. So the last part of what we need to do today is your favorite thing. Oranges. Also domain. Okay. Also domain. So we want to come back to this answer that we got and figure out the domain of that answer. Okay? Now, we're going to look at it in the calculator. But are we always going to have calculators? No, and in fact, today we do not. You'll notice that, right? They're using them for testing today. We don't have calculators to use today. So we need to be able to figure out a way to do this without a calculator. Only with our brain. But I have you in partners, so you can share brains with each other for a little while. That's fine. Okay? So, first thing I want to show you is I want us to remember what we talked about yesterday. Okay? Remember what we talked about yesterday? The square root of x? What is the domain of the square root of x? 0 to infinity, right? Starts at 0, 0 is included, and then goes to infinity. You okay with that? I want you to see this now. I want to do the fourth root, not that, the fourth root of x. You see it? It's that one right there. And then I want to show you the sixth root of x. And then I want to show you, what do you think? How about 8th? The 8th root of x? It's kind of going up right there, but then it's getting flatter quicker, right? It goes up a little further, but then gets flatter quicker. Okay? But what's true about every single one of these functions? The domain's the 0 to infinity, right? Well, what's true about each one of these numbers? What quality do they all have? They are all even numbers. Okay? 2, 4, 6, 8. Who do we appreciate? Yeah, you're right. It's okay. Okay? So what kind of domain, without me even graphing it, I want you to tell me the domain of a 12th root function. 0 to infinity. And how do you know that? Because it's an even number. Okay? It's an even number. Now, that's only if nothing is being added or subtracted to it, right? Because once we start adding and subtracting it, especially on the inside, it's going to move left and right, and that's going to change the domain, isn't it? So, but you know it's going to be from 0 to infinity to at least start with, and if there is something on the inside, like if this said x minus 2 on the inside, we would know we would need to move it to the right 2, so that would go from 2 to infinity, right? But this is our starting point right here. So looking at these two problems right here, what is the domain? That would be just 0 to infinity, right? Or x is greater than or equal to 0. Either way you put it is fine with me. Well, what about this one? How is this one different than this one? Only the number in front, and all that's doing is stretching it, right? Now this negative reflected it, but that didn't change the domain. This just stretched it more than this one, but it did affect its domain. No, a stretch does not affect the domain. So it just goes from 0 to infinity, or x is greater than or equal to 0. Guys, and we did that without even graphing. I mean, I graphed a couple so you could have that in your head, but we did the answer to these two without even graphing. We are amazing. Now look at these two. What kind of roots do these two have? Where's the root in these two problems? It's a 3, right? Remember the top is the power? The numerator is the power, the denominator is the root. This is a cube root. We talked a little bit about cube roots yesterday. So if I go back up to here, I keep thinking it's a touchscreen. I've done that like 4 times today. And people are like, Kingston, cut it out. I'm like, I'm sorry. Cube root of x. So there's the cube root. Do you see it? I want to make this one the 5th root. You see it? I want to make this one the 7th root. You see it? I want to make this one the 91st root. What kind of numbers am I choosing? Odd. So even 91st root? Is that still going to look like these other ones? It's there. You see it? It's stretched a whole lot. Almost looks like it goes up straight to there and straight over. We know that it doesn't, right? You can imagine that it doesn't. But I'd have to really like zoom in on that for you to see it really close, to see that it curves. Okay? But what's true about the domain of every single one of these? All real numbers. So tell me about the domains of odd roots. Infinity to infinity. Infinity to infinity. Now, here's the difference though. What about this if I took it and moved it right 4? What's the new domain? Infinity to infinity. What if I moved it left 12? Infinity, infinity. What if I moved it up 64? That's a good thing, right? Odd roots are going to give us infinity, infinity. Now, so that there's some other things that can impact what the roots look like, but we're not there yet. Okay? So for what we need to know right now, I want you to keep in mind that even roots have what kind of domain? 0 to infinity, unless it's shifted over one way or the other, right? But odd roots have what kind of domain? All real numbers. Okay? So there's 3 things you're going to need to be able to do on your homework today. This thing over here where we added, subtracted, multiplied, or divided and simplified to an equation. There is evaluating, like we did here with the orange. And then there's finding the domain, like we did with the purple. Do you have any questions on any of those 3 things? So you have the rest of the period to work.